Hello everyone, welcome to our channel Code with Sunny, and today we will be discussing the medium problem. Problem name is Contiguous Array and its index is 525, and it is the fourth problem of daily challenge for the month of February. Okay, so let me talk about first the prerequisites required to solve this problem. Like, you need to know the concepts of array very well, or you need to know the concepts of hash table and the idea of prefix sum, okay, to solve this problem efficiently. Okay, so let's begin. Given a binary array nums, return the maximum length of a contiguous subarray with an equal number of zeros and ones. Okay, so we need to consider all those subarrays, and let's find out the number of ones and zeros appearing in that subarray. And if their count is exactly same, then we are going to consider that subarray as valid subarray. And there are many valid subarrays present in this array. We need to find that subarray we need to find that valid subarray which is of maximum length. Okay, so I'm defining a valid subarray as subarray containing equal amount of zeros and ones. Okay, so there are some of the examples. We will be discussing those also. For now, let's look over the constraints that would help us to determine what type of solution this problem is going to demand. So you can see that maximum length of a maximum length of an array that has been given to us is going to be around 10 raised to the power 5. So obviously O of n square solution is not going to pass. So we would be either considering O of n solution, that is the linear solution, linear runtime, or n log n type solution. Okay, so let's begin to understand this problem first. Okay, so let's say we have been given some array, let's say 0 1 1 0 1 0 1. Okay, so this is the array nums that is being given to us. So the brute force solution, let us talk about first this one, brute force. Brute force solution would be like considering I, where is I is going to be the iteration variable for every I belong to 0 to n minus 1, where n is the length of this array, and consider every j belonging to I to n minus 1. Okay, so we would be considering every subarray in more formal case. Consider every subarray, and count is going to denote, let's say count of I comma j is going to denote the number of let's say the count is going to denote the difference between the zeros, between the count of zeros minus count of ones, z minus o. And if this difference count of ij exactly matching with the 0, then I comma j, that is the subarray I to j, is a valid subarray. So we would be considering the length of the subarray as j minus I plus 1. So we need to maximize j minus I plus 1 such that count of ij will be exactly 0, where count of ij is going to denote the subarray from I to j, and the difference, that is the amount of zeros minus amount of ones, would be exactly 0. That is, their count is exactly same, then the difference would come out to be 0. Otherwise the difference would be either positive or negative. Okay, so this is the brute force solution. You can see the worst case runtime is O of n square. So obviously this would not pass. So how we are going to optimize this runtime? So let's try to understand that one also. So let me first erase this one. So the first thing that I'm going to do is so let me talk about O of wait a minute. O of n log n runtime and O of n space solution. So this is the TC and this is SC. SC denotes space complexity and TC denotes the time complexity. Okay, so what I'm going to do is for every subarray, let's say I'm talking about this subarray. Okay, now you can see that for every subarray I can fix the endpoint of this subarray. So if you're not going to get it, no need to worry about. Let's say we have a subarray at I from I to j. Okay, note that this j is always going to vary from 0 to n minus 1. Okay, now for every j we can move I from 0 to like j up to j. Yes, so we can move I from 0 to j, but yes, we can always fix the right bound of the subarray. Like suppose we have fixed the right bound of the subarray, so let me write down over here. Okay, so I have fixed this right bound of this subarray, so let me write fixed. Now you need to find out the maximum subarray whose difference between the zeros and ones would be 0, and that would end at the that it would end at the least index L. So L is the left bound of the subarray, so L should be minimized. So let me speak out once again if you're not going to get it. So I have fixed the right bound of this current subarray, which is J. Okay, and I need to find the minimum L such that the L to J subarray from L to J has difference exactly 0 and L should be minimum. Why I'm minimizing the L? The reason is quite simple, because we need to find the max length of subarray. Max length of subarray. Max length of subarray having the difference as 0. Note that difference over here is nothing but Cz minus Co. Cz is count of zeros and Co is count of ones. Okay, so we need to minimize L by fixing this J, and L should be like the least, like L should belong to obviously 0 to J, and L should be minimum. Why L should be minimum? Because we need to maximize the length of subarray. And also the if we have found some minimum L, then difference must be exactly 0 for that L to J subarray. So how we are going to find out this difference criteria? Okay, so one thing also, I am fixing this J for every J belongs to 0 to n minus 1. So obviously this should take a linear time O of n. Okay, now we need to search the minimum L such that difference is exactly 0, and this searching would take a logarithmic time obviously for every j belongs to 0 to n minus 1. That's why this log of n term is going to be appended in the time complexity, right? So how do we find this minimum L such that difference, that is count of zeros minus count of 1, should be exactly 0? So what is the trick to find that? So as I've already said in the beginning of this video, that is we need to consider the prefix sum. Okay, so let me just erase it out, all those. Yeah. Okay, so consider the case like prefix sum. I'm talking about the prefix sum. So let's say the array elements are a0, a1, a2, a3, a4, a5, and you are going to consider only this subarray. Okay, so you can find the sum of this subarray always by considering the sum from 0 to 4 minus sum from 0 to 1, right? You can always find out this sum. Okay, now the thing is, we have already fixed our j, that is the right bound of the current subarray, over this position, and we need to find the minimum L such that this sum, you can see this sum must be coming out to be 0, because actually this sum is nothing but the difference will be coming out to be 0. Okay, so when this difference comes out to be 0, can you just simplify this equation? Note that 0, 4 and 0, 1 is the sample value that I have taken for a better understanding. You need to consider for the general case. So if difference is coming out to be 0, you can see sum from 0 to 4 must be matching with sum from 0 to 1. It means that whatever the value of prefix sum of this at this position, that is, let's say we are maintaining the prefix sum pre-sum array. So pre-sum of I, where I is 4 over here, you can see I'm talking about this position. So pre-sum of 4 must be matching with the value that is present over here, because this sum, we are going to say 0 to 1, must be matching with pre-sum of 1. it means that the prefix sum is going to be repeated at this position. Okay, so if the prefix sum is going to be repeated at this position, it means that subarray from this to this is going to hold the sum as 0. Sum as 0. Note that this sum is actually the difference, count of zeros minus count of ones, right? So whenever some prefix sum is going to be repeated again at some position, it means that there exists a subarray from let's say the prefix sum is repeated at this position 4 and the previous prefix sum was found at 1. So the subarray starting from 2 and ending up to 4 is going to hold the value of as 0. So let me first change the color if you guys have trouble in getting the same. So this sum would be 0. So whenever there is a repetition of the prefix sum, then we are going to find the sum as 0. Okay, so this is the key idea. So how do we consider, like we need to consider for the sum 0. So what I am going to do is whenever we are finding out the prefix sums, so whenever we are encountering the value 1, you will increment the prefix sum plus equal to 1, and whenever you are encountering the 0, you will actually do sum plus equal to minus 1. Okay, so when you consider a subarray, let's call this subarray like 0 to 1. So you can see you have incremented the sum as 1 for this position when you are getting the 1, and minus 1 for this one. So minus 1 and 1. So you can see minus 1 plus 1 is coming out to be 0. So this will give you the value as 0. Okay, so whenever you are facing the 1, you will increment the prefix sum, and whenever you are finding the 0, you will decrement the prefix sum. Okay, so let's understand this whole thing with the help of the same example, but I'm going to do some calculations to show how the things are going to work up efficiently. So you can see the prefix sum at this position would be like you are facing the 0, you will write down minus 1. Then you are facing the 1, you are doing previous value plus 1, which is 0. Then 1, it would come out to be 1. Then 0, you will decrement the prefix sum, which would be 0. And then you are facing the 1, you will increment it. 0, then you will decrement it. Then 1, then you will increment it. Okay, so we will consider our subarray j like we are fixing the right amount for every 0 to n minus 1. Okay, so let's start with fixing j over here. So if you will fix j over here, can you find any like if you fix j over here, so the prefix sum ending at this value is minus 1. So can you find any prefix sum which is being repeated right over here? You can see there are no minus 1 present over here. Okay, so it means that there is no subarray ending at this position whose count of zeros minus count of ones should be 0. There doesn't exist any subarray. Okay, so let's talk about fixing j over here. So the prefix sum ending at this position is 0. Can you find any other prefix sum which ends right over any of these places with value as 0? No, you are not going to find it. So we are not having any subarray ending at this position with count of zeros minus count of ones being same. So let's talk about this position. Can you find any subarray with prefix sum 1 being repeated? No, you are not going to find it. Now let's try to fix j over here. So if you are fixing j over here, you can see the prefix sum is coming out to be 0. And now here is the tricky part. You are always, like you have already been encountered this value 0. So it means that the sum starting from this one to this one will be always holding the value as 0. You can see the count of zeros and count of ones are same. Now let's try to talk about this position. You can see again this value is repeated. So the sum is actually for this subarray 0 1, it is 0. Now let's talk about this position. Now this 0 is already been occurred at this position and this position. Now which position you would take to maximize the length of the subarray? Obviously if you take this position, you will be having the subarray of this one, and when you take this position, you will be having the subarray of this one. So yes, so you would always take this one to maximize the length of subarray as asked in the problem statement. Okay, so you need to find the least L, and this can be done easily with the help of hash table by storing the frequencies. Okay, so if you want this logarithmic term to be reduced to O of 1 operation, you can also make a linear array of size 2 into n plus 1. Why I'm going to do that? Because the sum, prefix sum, prefix sum is always going to be like n, and it is always going to be between minus n to n. Okay, so it will be minus n to n. So we can always map the prefix sum, any prefix sum, in the range from 0 to 2n. We can always do that, because when we are going to have minus n, we will increment the value to n. Like every value is going to be shifted by plus n positions. Like if you are facing minus n, I will map it to 0, and when you are facing the value 0, I will map it to n. When you are facing the value n, I will map it to 2n. Like every value is going to be shifted by plus n positions. Why I'm going to do that? Because to make these values to be exactly fitted in this range 0 to n, because the any array or vector cannot hold the negative indices in C++. That's why I'm going to do that. Okay, so let's look out over the code. Okay, you can see I've done a lot of submissions. So first let me introduce with this logarithmic solution, then I will try to explain the optimization part. Okay, so I will take a map that will store the prefix sums. Okay, also you need to store for the 0th case, like you can have any prefix exactly having the same sum as 0, like the difference of zeros minus difference of ones, sorry, count of zeros minus count of ones as 0. In that case you need to consider the every like entire prefix, so you need to find that minimum L. That's why I've mapped sum of 0, that is when the sum is 0, as minus 1. Okay, so I iterate for every indices and try to fix the right bound of the subarray. Okay, so when I will iterate for that, when I face nums of I as 1, I will add 1 to the prefix sum, otherwise add minus 1. And when this prefix sum is already seen, you will find out the minimum L, which is pre-sum of sum, and you will find the length of the subarray, and we will try to maximize that. And if this sum is not seen, we will store the entry in this hash table and finally return the answer. So this will give you all test cases passed. So let's talk about this O of n times solution. Okay, so you can see I have made a scene like prefix sum that will store the mappings of prefix sum of size 2 into n plus 1, and for every prefix sum I will map them I will increment the value plus n to like increment the value by n. Why I'm going to do that? Because prefix sum can be negative, and we cannot store the values arrays like negative values in the array. So I will map the values to the I will increment the values by n, so that this can be fitted in this array. So I as in the previous case, you can see I will just have done like pre-sum of 0 as minus 1, but I need to do like scene of n over here, because every value is going to be shifted to the right by n place. So 0 will be shifted by 0 plus n. That's why I've done scene of n. So I iterate in this sum, and the entire process will be same, you can see. And when this sum is already seen, so I will search for sum plus n, because every value is shifted. It's not equal to int max, so it means that this sum has already been found. So I will try to find the minimum L, that is, you can see scene of sum plus n. And when I have found this minimum L, I will try to maximize the length of subarray. Otherwise, if this prefix sum has already, this prefix sum has not been found, then I will push back the entry, not saying it as pushback, I will store the entry of this prefix sum as the current index, and finally return the answer. So this will give you all test cases passed. So if you guys have still any doubts, do let me know in the comment section of the video, and thank you for watching this video.